All right, so this sheet gets us to practice sort of the fetch execute cycle, so we can kind of track how programs are actually executed, how these commands are moving through the processor, what registers are and aren't changing, as a program kind of is executed one machine instruction at a time. All right, so it says answer the questions in the section starting with the values above. So here's our starting program. A store 100 has just executed, which is why this 40 that was in the register is now showing up here at memory address 100. All right, and then we're going to look at each instruction, kind of see what happens, and adjust the values accordingly. All right, so if the program counter is at 5, we know when this next instruction executes, it's going to be 1 higher. All right. The instruction register is going to contain this code. So that's going to be the load 101. All right. Now, load doesn't change anything in memory. All right. It just retrieves a value. So we can count on these values in memory all being the same. So 40, 30, 10, and 50. And then the only thing that's really changing here is our general purpose register, because we've loaded 101. So where previously it was a 40 up here, now it's going to have the value at 101, which is a 30. All right, so comparing this box to the one above, the program counter is 1 higher. The register now contains a 30 instead of a 40. The instruction register contains load 101 instead of store 100. All right. Now we're going to keep going. Fill in the values of the memory cells after the following command is fetched and executed. All right, so after it's fetched and executed means our program counter's gone up by 1 again. All right, our instruction register is going to have the add 102 inside of it. Now again, add 102 doesn't impact memory, so we can count on all of these being the same. But what add 102 does is it does change the general purpose register. All right, it takes this value in 102, which is a 10, adds it to the register, which previously had a 30 in it. So now we know our register is going to have a 40 inside of it. All right, and you can kind of see how this is going to progress from here. All right, now it says fill in the memory cells after subtract 100 has been fetched and executed. So our program counter has clicked up to 8. Our instruction register is going to have that subtract 100 inside of it. I forgot my pound sign up there. Again, you can do it either way. I like putting the pound sign in, but if you forget it, it's not a huge deal. It's just to designate that it's like an address and not like adding the number 102 or subtracting the number 100. It just makes it more clear that we're referring to an address there. So anyways, subtract memory location 100. Again, isn't going to affect the memory, so this can stay 40, 30, 10, and 50. But it is going to take this value of 40 and subtract it from the register. So R, when you're doing subtract, it's R minus X. So in our case, it's the 40 minus 40. So our register is going to go down to 0. Right? And then if we look at this last one here, it says what's going to be there after we execute store 100. So our program counter has gone up to 9. All right, store doesn't change the register, so this time I can fill it in right away. I know it's still going to be 0. The instruction register is going to have that store 100. Now this time memory is going to be changed. All right, whatever's at memory location 100 is now going to have the value that was in the register, which is 0. So this is going to be 0. This is going to be 30. This is going to be 10. And this is going to be 50. All right, so again, just kind of tracing things as you move through a program And this is what's happening inside of your processor, all right? All of these values are getting updated. The program counter, the register, the instruction register, one machine language code at a time. And then this is probably what's in your RAM as the program is executing. And sometimes it's changing and sometimes it's not, depending on, the instruction that's actually executing. All right, so let's try one more of these. And this one's going to involve like comparisons and jumps. So being able to kind of follow along with that and understand how that's going to change the condition code register and the program counter and so on and so forth. All right, so here's our starting values. Our program counter's at 5, register's at 40, store 100's in the instruction register. Our CCR is currently all zeros, and then we've got the same 40, 30, 10, 50 that we had on the front page. All right, so same thing, fill in the values after the command is fetched and executed. So program counter was 5, it's going to go up to 6 after this has been fetched and executed, which means that load 101 is in the instruction register. All right, now load is taking something from memory and putting it in the register. So we know that memory hasn't been changed, but our general purpose register has. It now has the value in 101, which is a 30. All right, so that's now got a 30 inside of it. All right, our next instruction is compare 102. All right, so again, our program counter goes up. Our instruction register has a compare 102. All right, now compare doesn't change the register, so that's still got a 30 inside of it. It doesn't change memory, so that still has a 40, a 30, a 10, and a 50. But what it does change is the condition code register. So just remember that when you compare 102, that's comparing X on the left-hand side to the register on the right-hand side. Or in our case, a 10 that's in 102 to a 30 that's inside the register. Now 10 is less than 30, so our condition code register is going to go 0, 0, 1 to indicate that the comparison was a less than. All right, now fill in the values of the memory cells after the command is fetched and executed. So the command is jump LT17. Now, this says after the command is executed. So based on this, since the condition code register is a 1 there, our program counter isn't going up to 8, it's going all the way to 17. Now, if it had been a 1 here or here, then we wouldn't have executed this jump and the program counter would have just gone up to 8. But because the less than flag has been set to 1, when we execute this command, it's going to change the program counter to 17, which is going to affect the next line, that we end up executing in our program. But the register, again, a jump's not going to change the register, so that's still going to be 30. The instruction register is just going to have the jump LT in it, and it's jumping to memory location 17. All right, the condition code register doesn't automatically reset, so it would still have a 0, 0, 1. All right, that's not going to get reset until you do another comparison. And then again, a jump is not going to change the memory, so that's just going to have a 40, a 30, a 10, and a 50 inside of it. All right, and then the last command here is increment 100. So our program counter is going to go up from 17 to 18. Increment does not change the register, so that's still going to be 30. The instruction register is going to have the increment 100 stored inside of it. Condition code register, again, we didn't do any sort of new comparison, so that's still 0, 0, 1. Now, remember, the increment command in our language directly impacts memory. So the 40 that was in here has now changed to a 41, and then everything else stays the same. All right. So again, just kind of forcing yourself to think through the nitty-gritty details of what's actually happening in your processor and your RAM when a program is executing. All right. And that's really all computers do is they just repeat this fetch execute cycle again and again and again and again at super high speeds, doing super simple tasks, but combining those in ways that accomplish obviously some amazing things. All right. So hopefully this was helpful. If you have any questions, if you didn't get any of these answers when you tried it on your own, just let me know and we'll clear that up and you'll be good to go. All right. Have a great day.